Good morning. This is our STE video assignment. So for our topic is the application of stochastic differential system in SIS epidemic model. So SIS is we will explain it later. So now we proceed to the problem statements.
First is the problem statement. Some disease, in particular, some sexually transmitted and bacterial disease, do not have permanent immunity. So for this disease, the individual start up susceptible at some stage, catch the disease, and after a short time, the infection period becomes susceptible again. So for this disease, the susceptible infected susceptible SIS modules are appropriate. We extend this classical SIS epidemic modules from a deterministic framework to a stochastic one and formulate it as a stochastic differential equations SDE for the number of infectious individuals. Second is the objective of our project. Why we need to do this project for the disease? Because we need to formulate the SIS and the SIR, susceptible infected remove, as stochastic differential equations and Brownian motions. The second objective of our project is to discuss the perturbations by stochastic noise in the SIS modules.
Stochastic differential equation can be applied in many fields, including epidemiology, biology, chemistry, mechanics, microelectronics, economics, and finance. The main difference between the STE and ODE is the existence of the Brownian motion. The general form of the STE is as shown in the slide. For the stochastic differential equation in the SIS model, we denote that ST as the number of susceptible and IT as the number of infected at time t. Then the ODE, which describes the spread of the disease, are as shown in the equation in the slide, with the initial value S0 plus I0 equal to N, where N is the total size of the population among whom the disease is spreading. Mu is per capita death rate, and gamma is rate at which the infected individuals became cured.
So 1 over gamma is the average infection period. Beta is the disease transmission coefficient, so that beta equal to lambda over n, where lambda is the per capita disease contact rate. To establish our SDE model, we naturally rewrite the equation in the differential form as shown in the slide. Consider the disease transmission coefficient. Beta is the deterministic model. This can be thought as the rate of each infected individual make potentially infection contact with each other individual, where a potentially contact will transmit the disease if the contact is made by infection individual with a susceptible individual.
So Brownian motion, also known as mini process. So stochastic process WT is said to follow standard Brownian motion on 0 to capital T if it satisfies the following: W0 equal to 0 with the probability equal to 1. For 0 less than S and less than T and less than capital T, the random variable given by the increment WT minus WS is normally distributed with mean 0 and variance T minus S. So for 0 less than S, less than T, less than U, less than V, and less than capital T, the increments WT minus WS and WV minus WU are independent. So WT is almost surely continuous. So some stochastic environmental factor acts simultaneously on each individual in the population. So in this case, beta changed to random variable beta. So more precisely, each infected individual makes the following formula. So it means that beta dt equal to beta dt plus sigma dbt. So potentially infections context with each other individually in t to t plus dt. So here the differential of bt equal to b t plus dt minus bt. So it's the increment of the standard Brownian motion. Thus the number of potentially infections contacts that a single infected individual makes with another individual in t to t plus dt is normally distributed with means beta dt and variance sigma square dt. Hence the mean of beta dt equal to beta dt and the variance of beta dt equal to sigma square dt. So as the variance beta dt equals 0 as dt equals 0, this is a biologically reasonable model. Indeed, this is a well-established way of introducing stochastic environmental noise into biologically realistic population dynamic models.
As we explained just now, the deterministic SIS epidemic model is one of the simplest possible epidemic model and has application to transmission of real-life diseases. And it's also important to include the effect of uncertainty in estimation of parameters such as the disease transmission coefficient. And we also have looked at an SDE version of the classical SIS epidemic model with noise introduced in the disease transmission term. So, in conclusion, stochastic differential equation is applicable in epidemic field. Thank you.